We are still continuing on constraint addition. Yep. We were still talking about equality constraints. Okay. And then we looked at the first order condition, right? What is the first order condition? There is a condition. That means your the gradient of the point that could be a minimum is a point where the gradient of the function is a linear combination of the gradients of your different equality constraints. Okay, uh, that's one. And the second order necessary condition is again the Hessian that of both these, taking into account these are the Lagrange multiples. Right? This is strict. Okay. And y is from the tangent space of x star. If x star is the point which we are evaluating for whether it's a minimum or not, local minimizer or not. Okay. What is the geometric interpretation of this? What does this mean, geometric? Yeah, go ahead. Right. Correct. This could be a minimum or a maximum. But geometrically, what does this statement gradient of f plus gradient of h transpose lambda being equal to 0 mean? Well, see, the equality constraint h of x equals 0 represents a surface, right, in Rn. Okay. What does this condition mean? Well, the point, and we are only allowed to search on this surface. The point on the surface which uh, touches one of the contours of f of x. So f of this is what you're trying to minimize. Right? If you're talking about in n-dimensional space, um, the contours would be of dimension n minus 1. Okay, that's it. Yes. Two dimension is easy. Okay? If these are your f of x contours, and this is your h of x, and these are your f of x, and we are only allowed to search along this. Where is the minimum here? Minimum occurs at a point where this curve touches one of the contours exactly at one point. It does not cut through the contour. So that would be here. And this point would be the minimum. And the lowest value, so let's say if this is x star, the lowest value attained for f of x would simply be f of x. So that's the lowest possible value you can get for f of x. And the x that gives you that lowest value is the point that touches it like this. Okay? Right. And this statement essentially is an equivalent statement to this, because at this point, the gradient of f of x is pointing in this direction, gradient of f, right? The gradient of h has to be along this line. It might be pointing in either of the direction. Gradient of h also points in the same direction. In higher dimension, this simply means that the gradient of f is in the normal space of h of x at a point x star. Then that point is a potential minimizer of the function. Okay, and at that point, this condition is satisfied, or this, well, if it's greater than 0, then you know for it's a strict local minimizer. Okay, the second order condition. And then we talked about the inequality constraint. Straight. And the condition here was So you're trying to minimize f of x. No. This is your condition. This is your problem. And what is the first order condition according to? Well, it's simply an extension of this. So if x star is a local minimizer, then at that point the gradient plus 0. And what is the condition here? Here lambda could be any scalar, whereas here mu is always greater than or equal to 0. That's one condition. Second condition is that G transpose mu will be 0. Okay, that means mu is positive only for the active inequality constraints. Active inequality constraints are constraints where x star is on the boundary of that particular inequality constraint. If for the inequality constraints that are not active, mu would be 0. Okay. It would be positive for active constraints. Lambda can be any, well, lambda I is any real number, whereas mu I is less greater than or equal to 0. Okay. And there is a similar second order necessary and sufficient condition that you can look at the slides. Right? It's similar to what you have here. Okay. So this is we covered. Right? What we look at today is again something related to optimization, but it's a restricted set of problems, especially and in particular linear least squares. Okay. This often comes up in many applications, in particularly in data analysis, right? Where if you're trying to fit models for data that you've collected experimentally. Okay. To motivate this, okay, let's say you're doing an experiment, okay, and you are essentially controlling the input to. Let's say we have a system. Yes. Now let's say it's single input, single output. Um, so your input is A, output is B. Okay. Scalar. Both of them are scalars. You want to know the input-output relationship. Okay. So you let's say you have the ability to change the input to the system. You apply different inputs and you measure what is the corresponding output. And let's say we call the inputs AI, outputs BI. For the different I essentially is counts the different inputs that you're applying. Okay, so A1 maybe produces B1, A2 produces B2, so on and so forth. Let's say, and you've taken n measurements. Okay, that's your data. Okay, and your goal is to use this to fit a model that describes the input-output relationship. And let's assume that, well, the first thing you do is if you know nothing about the model, about the system, you would take this and then you'd simply do the scatter plot. Okay, let's say the scatter plot looks like this. Okay, that's n. Okay, well, it looks like, let's say this is A, this is B. Okay, it looks like there is a straight line relationship, and it's possible that the straight line actually passes through the origin. So what kind of a model would you propose, given that you've seen that the data is distributed like this? Okay, we'll say, well, it looks like there is a linear relationship between them. So you'll say B equals some, okay, some x times A. Okay, for here I'm choosing x as the slope. Okay, this is a reasonable model. Is it a correct model? Well, we don't know. For sure, if you use this model, the curve that you fit will not pass through all the points. Okay. Okay. It's possible that the underlying physics is like this, that B is in fact proportional to A with a constant, with a fixed constant of proportionality, right? But the measurements that we make is not clean. It comes with some measurement noise. Maybe you've made some mistakes here. You think you've applied A, but maybe what you've applied is A. And maybe there is some inherent noise inside as well that has nothing to do with the measurement noise. There is some system noise as well. So what you measure or what you see here is the underlying truth plus other factors that you have no information about, right? Which you'd simply treat as things that happen completely randomly because you don't have enough information about that. Right? See, then the goal would be, well, what did you do when you did experiments in your physics labs in your 11th and 12th? If you got data like this, yes, you do a best fit curve. Well, I don't know if you guys did use Excel to fit a line, but you take the ruler and then you roughly place it somewhere here, and then you roughly draw a line that kind of passes through the middle of all this. Okay? Say that's the best fit line. It's okay to do that if you have some a few data points like this. You take a graph sheet and then you plot them. But if you have a lot of data, then of course that is not it's not feasible to do it by hand. We need to come up with a way of automating it so that you can do it on a computer. So one thing we can do is okay. And when you say you're drawing that line, right, and you've decided that the line has to pass through the origin because that's the model, and you keep this ruler and then you turn it around and then see which slope gives you the line that passes through more or less through the center of this distribution of points, and then you choose that as your x. We'll essentially do the same thing, but we'll pose it algebraically so that we can then write a program to do that process on a computer if this data is available as a bunch of numbers on your computer. Right? So what you'd say is for sure, there is no x that will pass through all of these, right? Okay. If I had only made two measure, or in fact, if I had made only one measurement, right? Say I get this A1, let's say I stopped at A1, B1, and I want to fit a model like this, then for sure you'll get a model that will exactly pass through your observation, right? Because you've constrained the model to be like that. That means if I apply 0A, if A is 0, B is 0. So this you anyway you know because of that model. You simply draw this line and say, this is the model for my system. And you get perfect fit. Okay, that's because you have one unknown and you have one measurement, so you can solve for this equation. Okay, so, and what will be x? X is this. X will simply be d by a. That's fine. But the moment you make multiple measurements, right, right, like we've done here, there is actually no x that will solve this problem. Okay, because if you draw a line that passes through this point, then it's not going to pass through the others, and so on and so forth. Okay, so the best we can do is find an x that, on an average, uh, is close to all of them. It's not too far away from any one of them. Okay. Right. So the one way to say that is, okay, there is no x solves solves this where a b1 equals x a1, x a2, and so forth. Okay. There is no x that will simultaneously solve all of them. Okay. This should already remind you that, well, if you have n equations like this, each one is linear. We should be able to write this in a matrix form, right? How do I write this? So I will say a1, a2, an multiplied by x equals okay. You have more equations than okay. When can you solve the system like this? Going back to one of the initial modules, maybe module 2 or 3, module 3, Paul metric, exactly. When do you, let's assume this is full rank. That means all of them are not zero. When can you solve a tall system? Or what are the possible solutions for something like this, where A is infinite? Hold on, if A is tall, do you have infinitely many solutions? Okay, you will always have a unique solution. Yes. So this is exactly you will have a unique solution. Assuming A is full rank, you will have a unique solution if B belongs to column space of A. What if it does not belong to the column space of A? Okay, then there is no X that will such that AX equals B. This cannot be solved. And that's often what we will have because of noise. Okay? And this is an example. So if, let's say, we were dealing with the ideal scenario, there is no noise. Our measurements are perfect, and the ability to control the input is perfect. And the true physics was in fact like this. Then what would happen is B would be in the column space of A, which simply means B would be a scaled version of A. Okay, and that scaling factor would be your the system parameter X. Okay, but in general it's not. That means B is not in the column space of A, but it's deviated from it. Okay, so we cannot exactly solve it. So we say, okay, what value of X can I find such that if I multiply that X by this column, the difference between those two columns is as small as possible. Okay, right. So let's say I call that the error E. I cannot solve it exactly, but what I want to do is find the difference between. So this is A, this is B, and this is your H right. Okay, I want to minimize this, but of course I don't care about the sign. Positive and negative signs for the error are okay, but the magnitude has to be small. Okay, for now, I mean, of course, how do we find the magnitude of a vector? Can you only use the 2 norm? It doesn't matter. You can use any valid norm, but for now, let's say we're going to use the 2 norm. Okay, that's what I do. Well, I'll not call it my error. I will call this uh, now. Notice I've called it f of x. Okay, the unknown here is x. Okay, that's my system parameter. A is measurement, B is measurement. Okay, so the thing that is variable here is really x because A and B come from your experiment, the table. Okay, so your goal is to now find an x such that this is as small as possible. So again, optimization problem. So what we want to do is find x such that f of x is minimized. Okay. For now, there is no restriction on x. So this is an unconstrained optimization problem. And the problem is essentially this: minimize the b minus. This is the problem. And x belongs to Rn. Well, in this case, x belongs to R, but the general problem is like this. Okay, if instead of one input there were multiple inputs here, but let's assume there was just one output. Okay, then this each of that equation, let's say there were n inputs. Okay, the general case would be again a linear model. That let's say you have there are n inputs a1, a2, an. This is your y system, and let's say there is a parameter associated with each of these. Okay, and the model that you're building is essentially this y equals your a1, a2, a3, an multiplied by. These are your parameters. This is your output and this is your input. X tells you how much the first input, if you change the first input by 1 unit, how much the output would change. X2 tells you if you change the second input by 1 unit, how much. Okay. So you have n inputs now. So now you do the same thing. You build a table like this, except now you have n input columns, okay, and one output column, an, a2, a1. Let's say you're doing m measurements. Okay. I should not have called this n. Let me call this m. Okay. Let's say we're doing m measurements. You apply A11 as the input for the first experiment. You apply A11 here, A12, A13, and so on and so forth. A1n, and you get B1. You apply A21, A22, A2n, B2, and the last one is AM1, AM2, AMN will be it. Okay. Now, you can express this as x equals b, that this belongs to what? What is the size of b? R, Rn. This one, Rn, and process. Okay. Now, we want to find, there again is no x that will fit the whole thing because right now we are only talking about the case where right, b will not be in the column space of A, so this cannot be solved. So we are willing to accept not an exact solution, but a solution that is that takes Ax as close as possible to B. Okay, so essentially we are saying minimally same thing, right? That was for the one-dimensional case. Here, this is the generalization where X is now belongs to Rn. There, it was just R. That's the general problem. We know how to solve this, right? Unconstrained optimization. This is f of x. I can write this as simply b minus ax transpose x, right? Tell me what you will get if you multiply this out. That will be my f of x. Okay. Once we do that, then we compute. Okay. Sorry, what is it? Yes. Hey, hold on. What is, okay, if this is a vector, right? Why do you say x transpose x is x square? Is there a square operation defined for a vector? Okay. So what does that expand out to? Well, you can take the transpose inside. So what will happen if you take the transpose inside? Ax whole transpose, which will be A transpose B minus Ax. So if you multiply this out, what will you get? How many terms will you have if you multiply this out? Yeah, tell me. So what will be the first term? There should be 4 terms, right? Because there are 2 here, all possible combinations of their products. Oh, yeah, sorry, yes. Yeah, that's what you were saying. Okay, got it. So it'll be B transpose B. Yeah. Okay. See, these two are scalars. Okay. That means the order of the inner product, at least with since we're dealing with only real vectors and real matrices, the order does not matter. That means you can club this together and simply write B transpose B minus 2 times B transpose AX plus X transpose A transpose A. Okay, that's your f of x. This is what you're trying to minimize. Is that clear? Okay, this is what you're trying to minimize to fit this data to a model like this. Okay. In an unconstrained optimization problem, what is the first order condition for okay? The condition is at the point where it's a minimum. Let's say the point that we are talking about is x cap. If x cap is in fact the minimum, then this should be equal to 0. What is the gradient of this? What is the, okay, gradient is a linear operation. That means you can apply it individually to each of these three terms. What is the gradient of this with respect to x? 0. This is fixed. Okay, so that's so so this is what we want to do. So f of x cap will be, first one is 0. What about the second one? Okay, if you do B transpose A, right, you will get a row vector. Okay, I'm going to flip it. Okay, 2 times, okay, the transpose of that. Get this. What about this? Okay, well, this is like ax, the derivative of ax is a. This is like ax square. So what you will get is, you will get a column vector. Okay, what you will get is 2 times, because there are 2 x's. Okay, you will, this is part of your assignment, so you will when you do by hand, you will know why it comes out this way. But for me, just trust what I'm saying now and then assume that this is correct. What you will get is this. So this is like ax square, so it's 2 times ax when you take the derivative. Okay. And this has got to be, and this is at x cap, so equals 0. That means, well, the 2, I have 2 times A transpose A x cap minus 2 times A transpose B equals 0. Okay, I can take the 2 out. The 2 does not play a role here. And I can move this to the other side, then it becomes equal. Okay. Now, we will make an assumption. Okay, we'll assume the rank of A is the tall matrix. It's full rank. So what should be the rank of A? M is greater than n, right? That means what is the size of A transpose A? N cross n matrix. It turns out that if A is full rank, if a tall matrix is full rank, then A transpose A will also be full rank. Will have rank n. Okay, this is easy to show, but I won't show it. Okay. That means now we have a square matrix that is full rank. That means this matrix itself is invertible, right? Now, if I multiply both sides by the inverse of this matrix, then I get, well, there is a name for this. This is a very popular equation. This is called the normal equation. So when somebody talks about the normal equation, this is what they're talking about. And because A transpose A is an invertible matrix, x cap is simply A transpose A inverse A transpose B. Okay. You've seen this somewhere, right? That's a pseudo inverse. Okay. So if x cap, uh, well, if x cap is satisfies this equation, then the gradient is 0. So it could be a minimum. Okay. A transpose A inverse A transpose B. So this could be a minimum. How would we verify that it is in fact a minimum and not a maximum or a saddle point? Okay. We need the Hessian. What is the Hessian of this? Of f of x? Well, you have to take the gradient again of this. Yes. So the Hessian of f at x cap is simply 2a A transpose A. And what is the condition on the Hessian for this to be a minimum? This should be greater than or equal to 0. What does that mean? Is it a positive is this a positive definite matrix? It's full rank. Okay, that means its null space is empty. It only has 0. That means if you take A transpose A and you multiply it by some vector on the left and the transpose on the right, well, this has no null space. That means this product itself can never go to 0. Okay, so that's for sure. So what will come out will be a non-zero number. But if you look at this, right, this is nothing but AX multiplied by AX transpose. Right? This is A transpose, X transpose A transpose, which is essentially AX whole transpose. Now I just said A does not have a null space because it's full rank. That means this cannot be 0. I mean this cannot be 0. If the inner product of two non-zero vectors has to be, well, not even equal to 0. It has to be greater than 0. Okay? That means this is in fact positive definite if A is full rank. That means this is in fact a minimum. This is a strict minimum. Strict, well, strict local minimum according to the conditions. But in fact, this is a case where this is also the global minimum. This is a unique global minimum. Right? So in fact, for the uh, the solution to this problem is in fact you can find the global minimum for this for the unconstrained optimization problem, and the solution is essentially this. This is one of the few problems where you have an exact analytical solution. You don't have to resort to any sort of iterative methods. See, you might still resort to an iterative method because assume that the model is huge. You've got 10,000 inputs or 100,000 inputs. That means the size of this matrix would be, let's say, 10,000 by 10,000. That might be a huge matrix, and you need to take the inverse. So you might still resort to iterative methods by saying, okay, I will take a sample of these, fit fit a model, and so on, and do it iteratively uh, to get a better estimate of x cap. But when you can do this numerically without any problem, then you do have an exact solution. Okay, all right. And now, well, that's the best possible system parameter. Okay. Now the question is, what is my error itself? What is f of x cap? F of x cap now simply will be the mod of b minus x cap square. That's the smallest possible value for f of x. You cannot lower it below this. Okay, for this particular model. Okay? And let's say this, we call this b cap. Right? Even though b does not belong to the column space of A, b cap does, right? Because b cap is simply A times x cap, some vector x cap. That means you're taking the linear combination of columns of A. So b cap actually belongs to the column space of A. Right? So all we've done is, imagine this is the column space of A. Let the origin is somewhere here. This is a column space of A. Okay, and the space here will be Rm. Okay, you have whole of Rm, and then because you only have a few, you don't have so you have n columns, which is less than m. That means you're not spanning. You cannot span all of Rm. You can only span a n dimension. So this is an n dimensional subspace of Rm. Okay, and your vector b was not on this subspace. It was outside, somewhere here. It was pointing outside the space. That is why you could not solve it exactly, right? This was your b, but this b cap lies here. Okay, b cap is here. Okay? And this b cap is obtained by minimizing the distance, the two norm of the error vector, which is this. That's the B minus B cap vector. Okay. We've seen this before, right? Where if you have a vector and you have a subspace and you want to find the vector in the subspace that is as close as possible to this other vector, and the distance is measured in terms of the two norm, that resulted in a specific operation, right? So it turns out under the two norm condition, this B minus, let me write it down, this B minus B cap will actually be orthogonal to B cap. Okay, so all you've done here by computing X cap using this formula and then multiplying X cap, so you found out X cap using B and A, and then you multiplied it by A, which essentially gave you A transpose A inverse A transpose B. All you've done is you've done an orthogonal projection of B onto the subspace spanned by A. Right? So this is nothing but the, the orthogonal projection matrix onto the column space of A. Okay. When we talked about orthogonal projections, what did we need from the subspace to come up with the projection matrix, orthogonal projection matrix? You needed an orthonormal basis for the subspace, but here is some basis. The columns of A form some basis for the column space of A. They're not orthonormal. Okay. If you have an orthonormal basis, if you had an orthonormal basis, let's say to the column space of A, let's say I call that B. The columns of B form an orthonormal basis for the column space of A. Then how would you have obtained the orthogonal projection matrix? Yes. This would have simply given you that. If you don't have an orthonormal basis, then and you have a general basis for the subspace onto which you want to orthogonally project, then this is a projection matrix. And in fact, you can verify that if the columns of A were orthonormal, this will essentially be I. You can verify that. If this is I, this is gone. What you're left with is A transpose. That's exactly what I've written there. One way to think about this, if you have an orthonormal basis, this is what you do. You do the same thing here. You have A transpose, but you have something in the middle. Okay, you can think of it as, okay, you still do A transpose, but you insert something in the middle to account for the fact that they are not orthogonal to each other and they don't have unit length. That's all. Okay. All right. So this problem of fitting a linear model, okay, X equals B, where we have no parameter that will exactly fit B, is essentially a problem of orthogonal projection. Okay. Now, you're probably thinking, okay, that's fine. It sounds okay for a simple linear model like this, where Ax equals B. Okay. It seems like a fairly simple model. If you have multiple inputs, then you're saying A1 x1 plus A2 x2, An xn equals B. Now, it turns out that this actually has a broader application, because the requirement here is that the input-output relationship of this system, A1, A2, An, for you to be able to use this method to fit a model, what you need is the relationship between the x's and b has to be linear. Okay, so that means you for example, we know how to fit this. Okay, a model like this. What if you had a model like this? Well, ax plus Well, let's. This is a model like this. The AX model is this. This is a model with a y-intercept that does not pass through the origin. How would we fit this? Using the same procedure. There is only one input, but there are two parameters. Well, all you do is you have A1, A2, AM. These are the inputs that you applied. And then you choose the second column to be all ones. And then you say, I have two parameters for my model. It's two. And then I have my B. So you can use the same procedure and fit, except now your A is slightly different. Okay, right. This is one. What if you have something a little bit more fancy? Let's say polynomial equation. Let's say the input-output relationship is actually polynomial. Okay, let's say the input is still only one. You have a single input, B, but B is related to A like this. Well, x1 A square Q x m A power n. Okay. This is also no problem because the relationship between B and the x's is still linear for a fixed value of A. Okay. Then all you do here is, again, let's say you apply different inputs. Now your A matrix would simply be A1, A1 square, A1 cube, A1 m, and you have A2, 2 square, A1, A2 cube, A, sorry, this is, I did a mistake. This is n. There are n parameters. A to n, and then you have am, am square, am power n, multiplied by x1, x2, xn. You can also fit a polynomial model. It does not have to be like this. It can be something more complicated. This could be sine of A. This could be log of A cube. Maybe if A, all the A's are positive, this could be square root. As long as your parameters have a linear relationship to B, you're fine. You can fit nonlinear models as well. Models that are nonlinear with respect to the input, but not the system parameters. So if the system parameters are linearly related to the output of the system, then you're still okay. Yeah. So this framework does, the linear least squares framework does have a broad application and not just simple x simple uh, x equal to b scenario. The input output could be non-linearly related. The parameter has to be linearly related to your output. All right. So that's the basic linear least squares. See, but often uh, in applications, you will find that there isn't just this one objective that you're trying to minimize. There might actually be multiple ones. Okay. Maybe you're trying to get the best machine for the lowest cost, okay, and minimum or maximum efficiency. But let's say smallest machine, maximum. Right? So you could have these multiple uh, criteria, some of which you want to maximize, some of which you want, some of which you want to maximize, some of which we want to minimize. And often it will turn out that there will be conflicting requirements, because if you go for a smaller machine, it's going to cost more. Maybe it's more efficient, but Again, if you go for more efficiency, maybe it's going to cost more. Maybe if you want more efficiency, maybe you have to go for a bigger system and things like that. Because if both of them are not conflicting, then you're effectively just optimizing one, right? So often we have um problems where you've got multiple criteria that you're trying to minimize or optimize, and they will be conflicting. Right? We'll again look at how or one method of dealing with something like that. Right? Let's say I'm going to instead of having one f of x we were trying to minimize or optimize. Let's say there are these multiple okay, because we are only focusing on linear a squares. Let's say all of them are of this form: a1 x minus b1. So my first criteria involves some a1 matrix and b1 matrix and relates to my x this way, and I need to minimize these two. The second one could be a2 x minus b2 square a3 x. So if you have these conflicting interests, how do we deal with this now? Remember, each of them is a scalar. You say, okay, fine, I have these multiple uh, requirements or functions that I need to optimize. Let's say all of them have to be minimized. You could say, fine, then I will take my f1 of x, I'll take my f2 of x, I'll simply add them together. Okay, and I say I want to minimize this whole thing. Okay, that's one way to do that. Okay? Now this whole thing is your f of x. You still come back to the problem that you know how to solve, minimize f of x, where x is any vector from Rn. Another thing could be, well, you could say, okay, I care about f1. I, I care about this particular error more than this error. Okay, and I care about this more than the third constraint, and so on and so forth. Right? That means I want to find an x that brings a1x closer to b1 then and I'm willing to uh, allow a2x to be slightly far away from b2. That's what I'm saying when I say I care more about f1x. Right? So one way to code that into your optimization function is to say, okay, is to multiply each one of these by some scalar, row 1, row 2, row k, and each of these rows will be greater than or equal to 0. Okay, well, let's not say 0. If it's 0, then you're saying I don't care about that. They're greater than 0. Okay, and depending on the size of the row, you're saying I give more weightage to that. For example, if row 1 is much, much larger than these, then your optimization problem, well, then your optimization algorithm is going to care more about the difference between a1x and b1 than the other ones, because if it reduces this by a tiny amount, the reduction you'd obtain would be row 1 times that tiny amount, which is a much larger reduction in f of x than if you tried your best to minimize these things by a large amount. Okay, so that's how your rows control what you care about. This is one reasonable way of doing carrying out this optimization problem. Okay? So let's assume just there are two of them, right? f1x and f2x, right? So, and we can say f of x is simply row 1 okay. Often what people will do is they'll say they will set this to 1, or you divide the whole thing by row 1 so that you get row 1 here. That means you give a weightage of 1 here, and the size of this determines whether you give more weightage to this, less weightage, or equal weightage. If the ratio is 1, then you give equal weightage to both of them. If the ratio is huge, that means you give more weightage to this. If the ratio is very small, that means you really don't give as much weightage to this compared to this. Right? The ratio is simply the relative weight compared to the first objective. That's another way you might see this being written now. You might also see people write it like this. If you have only 2, then is another way people will write. Okay? And this is the relative weight of this uh, optimization, this error function compared to this. Okay? It turns out that this also can be made to fit into Ax equals B model in a slightly different form. Okay, this is simply a scalar, and this is a scalar, but it's squared. If you simply take rho inside, it becomes square root of rho, right? So you can rewrite this in this form. So your f of x will be simply rho 1 a1 minus rho 1 b1 plus rho 2. The square root is okay because we've assumed that the rows are all positive numbers. You can further simplify this. I won't go into the details. You can actually write this as sum a tilde divided by x cap minus, and your a tilde is simply this. You can verify this later by yourself. So and your b you can later on verify that this is a block matrix, that you can actually stack it like this and all. Okay. If this is the case, how do we solve for x cap now? The value of x that will minimize this function based on what we just saw earlier. What will be x cap now that minimizes this combined optimization problem, what is it called? Multi-objective optimization problem. Well, a is replaced by a tilde, that's all. But what is the condition for this to be okay? For us to be able to do it like this, solve it like this, or for this to be correct? Well, the inverse has to exist. Okay, the inverse will exist if this is full rank. Okay, and it turns out the condition is actually quite simple. As long as one of the A's is full rank, you're guaranteed that a tilde will be full rank. Okay, that's a condition you remember. So a tilde will be full rank if one of the AIs, or in this case two A1, A2, one of them is full rank, then this is okay. Then you can solve it like this. Okay. Now the question is, how do we choose this ratio? Let me call it rho. Okay. If I simply called it rho, then of course there will be no rho 1. This will be 1. This will be square root of rho. Right? That you're clear. Now the question is, hold on. We're saying we've solved this, but the solution that I get depends on what I choose here, right? If I choose rho to be 0, okay, then the solution I would obtain for x cap is something that minimizes this error, and this could be huge. Okay, but by setting rho, you're saying I don't care about this error. But if you make this a huge number, then the solution that you would obtain would be the value of x that you would obtain would be the one that minimizes this error. And if you choose a value in between, then the solution that you obtain would do not a good job here, not a good job here, but on an average, it does the best job it can. Okay, so if you have multi-objective problems, your x cap does depend on the rho that you choose, and the way you choose rho is application dependent. That there is no algorithm to choose it. You have to you have to think about the application, see what these things mean, and then think about, okay, how much of an error here is bad for me compared to an error here, and then make a decision on rho based on that. I'll show you an example. Right, okay, here. So I am, J is simply f, okay? I've simply used J here, but f of x is what I mean here, right? Two objective functions just like this. Row 2 by row 1 is what I call row here, right? And what I've done is I have some A1, B1, A2, B2. I've chosen different possible values of rho, starting from a very small value, 10 power minus 5 to 10 power 5. And when rho is 10 power minus 5, then the solutions that I obtain here, there are three x's in I'm dealing with three parameters, right? I get some value. These would be the parameters that would minimize J1. Okay, that's the best possible J1 you can obtain. When I choose a very large value for rho, then I get a very different value. I get a very different set of values for x, and these would be the values that will minimize J2 to the maximum amount possible. And for values in between, you get some value in between. Okay. So this is one way to look at what kind of solutions do I get by simply turning this knob. Another way to look at it is a plot like this. Okay. See, you won't be able to do something like this for dimensions more than 2. I mean, 3 you can still do it, but it won't be as easy to visualize, right? But this plot at least gives you some idea about how to deal with problems like this, multi-objective problem. Right? So let's say we're talking about this problem. Okay? I don't know what value of rho to choose. Okay? So what I do is I run this optimization problem for different values of rho and find my x cap. And for each of those x cap, I find this value, the error that I make in my f1x and f2x. I plot f f1x here and I plot f2x. Okay. And it turns out for linear optimization problems like this, you'll always get curve that looks like this. Okay. So this is essentially the at any point, right? You get some value for f2 of x, some value of f1 of x, and for that value of rho, this is the best possible value you can get for f2 and f1. Okay. If you change the value of rho, then you come here. Of course, if I make rho very small, maybe you can tell me, if I move along this curve, to move along this direction, would I have to increase rho or decrease rho? To increase it, why? Let's say I'm here. If I increase rho, will I move in this direction or in this direction? I'm increasing rho. Well, if you say this, I don't know. This way. Okay, why? You're right. Why would. Well, if I increase rho, that means I care about this more. So my optimization is going to try to reduce f2 of x. That means moving along the curve in this direction would lower the value of f2 of x. If I lower the value of rho, then it moves like this because I care more about f1 of x. Okay, okay. Right? Now, so that means you can now trade off between your first objective and your second objective simply by turning the knob on rho. Okay. If you let's say this is one possible curve you could have gotten. Let's say we got a curve like this. Here, it means if I turn my knob, I lose some. If I decrease my rho, I'm here. I decrease my rho, I lose. Sorry, yeah, I gain in f1, but I lose in f2 because at this point, f2 is larger, but f1 is this point. F1 is lower, but f2 is larger. Okay, this is one scenario. On the other hand, let's say I had a scenario like this. Okay, and I was here. Okay. Would it make sense for me to keep lowering rho from this point compared to here? Here, if I turn rho, I always lose some amount. Let's say this slope is -1. The amount I lose in f1, I gain in f2. Or the sorry, amount I gain in f1, I lose in f2. Whereas here, so this means, so I'm here at this point, I get some f1 and I get some f2. But if I move from here to here, right, I actually gain a lot of f1 without losing a lot on f2. So it would actually make sense for me to turn my knob and go to this point. Similarly, if you're here, it would make more sense for you to be here. And around here, it's not clear. You gain and lose by almost the same amount. So here it really does not matter. It's probably a matter of taste. What you want to keep, what you want to decide is a good row. Okay? And and whenever you have a curve like this, right? This curve is the term that is used is called optimal curve. I think is that what it's called? Optimal solution or curve. Okay. These are all the best possible solutions you could obtain for solving this problem, because any point here, right, is not necessarily better than another point. Because see, you would say a solution is necessarily better than another solution if that's, for example, let's say I was here, right? I have, let's say I have solution 1, solution 2, solution 3, solution 4. Is solution 2 necessarily better than solution 1? Well, you move in this direction, that means you're lowering f2, you're lowering f1. So it is definitely better than this. So if I was given two options, I would always choose 2, because 2 has lower value for f2 and a lower value for f1. Okay. Uh, what about 1 and 3? 3, I slightly gain on f1 and I gain a lot in f2. Let's say this is here. 4 also I would choose because I'm gaining a lot of f1, maybe a slight decrease in f2, right? But what if you had to choose between 4 and 3? Well, it's a matter of taste, because if you go from here to here, you've gained f1 but you've lost f2, right? And that is what Pareto optimal means. That means these are points where there is no unanimous way of saying one is better than the other. Okay, 2 is definitely better than, see, 1 is the worst of all of them. 2 is definitely better than 4 and 3, but 2 is something that cannot be reached, because this is the best we can do by turning row and by solving the problem. This is essentially the boundary. Okay, so you can choose any points on this, and there you're essentially choosing what are Pareto optimal solutions. That means one is not necessarily better than the other. If you move from one point to the other, you're gaining on one objective, losing on another. Okay, that's it. So if you had multi-objective functions, these are things that you would use to arrive at an appropriate row for deciding what is the best possible solution. Okay. See, here again, I've assumed that a unit change here means the same as unit change here, so that you will have to take into account the units as well. Maybe finally everything will come down to cost. Then maybe it's easier. Then the units are all the same. So let's say you have f2, that's, let's say, cost of the drug. You change that into currency. Let's say this is amount of time the patient has to stay. Let's say you convert them to currency, then it's easier for you to decide which point you choose. That way, the units are all the same. Okay, all right. That's all I wanted to say about multi-objective function. We'll look at two more topics fairly quickly, and then we're done. Well, maybe we won't be done today, but that's okay. The next one is okay. If this was tall and we had to find uh, a solution for this such that Ax is as close as possible to B in terms of the second norm, then we said the solution is this: A pseudo inverse left pseudo inverse B. Okay. But to get but to compute the pseudo inverse, A had to be full rank. Okay, what if A was not full rank? What if A is less than? Okay, you remember what happens? Well, if a rank of, let's say B is not in the column space of A has got a rank lower than M. Of course, you still cannot solve this, but you can still find the closest possible X to B. The only problem is there are infinitely many X's that will give you the closest possible solution. Okay, it's a mix between tall versus uh, a fat matrix. Okay, so you can still solve this. Okay, it's just that there are infinitely many solutions. Okay, so people said, okay, fine. Then we will convert this into a multi-objective function and say there are infinitely many x's, but I want the smallest x possible. Okay, so you still define your objective function x. Okay, and then you say fine, this is not full rank, but then I say I want to solve. There are infinitely many solutions that will give me this. Okay, and I say, and I put a second objective function saying, okay, I want the solutions. Well, I want to minimize this, but I also want to minimize this, where I'm saying I want the x to be not too large. Lambda is some again positive number. Okay, similar to that. Lambda is rho essentially. Okay, maybe I'll use rho. Well, we know how to solve something. We know how to solve a multi-objective problem. What is A1 here? If we were to use that framework to solve this, what is A1? Or A2, sorry. This is A1, B1. What is A2? A2 is I. I. What is B2? That's all. Okay. So you essentially now form A, I. Well, no, this is B. So, okay. And if you work this out, what you will get, if you work this out, what you will get is this x cap is simply be A transpose K plus rho times I inverse A transpose K. We've seen something like this before. Well, this sort of, so whenever you add a term like this is called transition. Okay. In this particular form, where you use a two norm here, it's called the Tikhonov regularization. You can have other norms as well, but if you use the two norm, this is what it's called. Okay, but this we've seen somewhere else, no? Something like this, where A transpose A is not full rank. That means it's not invertible. It's positive semi-definite. So we we slap on a rho times I to make sure that this is now invertible. And in fact, it turns out that this is actually invertible. Sorry? Exactly. So we've seen something like this in the Levenberg Mark 1. Okay. All right. That means now, in fact, if we have AX equals B, and this is a fat or wide matrix. Okay. You can, well, we can solve for this already. But if you wanted to solve for this, but keep this small, okay, you can essentially solve the problem like this. Okay, to get the smallest possible x, that gives you that gives you Ax equals B. Right. See, the last topic, I think we will be done. I won't go into the details. I'll let you work it out. I will show the slide. Right. This is a constrained linear optimization problem. Again, I won't do it. The expression is there on the slide for you to uh, see, but I want you to try and derive that by yourself. And the problem we are trying to solve is essentially minimize this. Okay? But it's not an unconstrained problem anymore. There is a constraint. Okay, we have to choose your x. We can only choose those x's that satisfy this. Okay, A is m cross n, C is C cross n, and of course here, otherwise it does not make sense. Okay, because if C was n cross n and full rank, there is only one x that will solve it. There is no, there is no, well, the minimum possible value is the solution for Cx equals D. Okay? So I want you to use the Lagrange method. So this is equality constraint. Your How many equality constraints do we have here? This is a P cross n matrix. P, we have P equality constraints. So you should uh, so you use the Lagrange method to try and, well, arrive at this particular expression that you see here. Okay? So if you simply take the gradient of f of x, gradient of h of x, and you equate it to 0, you'll essentially arrive at that. Okay, okay, that's all I wanted to say. So this was again all maybe too very abstract. In the next lecture, we will look at a few examples where you can apply these techniques for solving problems in signal processing, image reconstruction, and maybe also some FEM, maybe some very simplified finite element methods for different applications. Okay. Are there any questions? Nothing. Okay. All right. Then we'll stop here and then we will continue on Monday. Okay. I'll try and release the assignments in the next couple of days for optimization.